Gentlemen, I am Dr. Frank Summers of the Space Telescope Science Institute, and it is my pleasure to welcome you here on this special night. As you can see, we are 1 week late. It is January 13th and not the second Tuesday, not the first Tuesday. But you can also see you got the really cool new seats and the wonderful new carpeting. They finished the auditorium retrofit, which is why they didn't let me have the public lecture series last week, which was good because I was in Seattle, Washington last week for the American Astronomical Society conference, so I wouldn't have been here had we held it last week. So it's great that both you and I can be here tonight, especially since I'm the speaker tonight. For those of you who came in, who haven't been here before, we have lithographs over on the table over there. If you did not get one on your way in, grab one on your way out. The lithographs are of the galaxy cluster Abell 2744, a very large cluster of galaxies, so large it produces gravitational lensing and is being used as part of the Frontier Field Survey, a little bit of which I will talk about in my talk tonight. Speaking of which, I am the speaker tonight, giving my 25 years of Hubble. I had actually expected to do this talk in April because the 25th anniversary is in April. But we decided to get the festivities going early, right? We actually released the major 25th anniversary image last Monday at the AAS meeting in Seattle. And so I said, all right, great. If we're going to do that, I might as well go ahead and kick off the year with the 25 years of Hubble talk anyway. It's also kind of difficult to get a January speaker. Nobody wants to commit to doing the talk after the holidays. This has happened to me every year. I've been running the public lecture series for 13 years now. January and July are generally the hardest months to get people to come in and do the talk. Okay, upcoming, we do have other talks upcoming. Next month, February 3rd, Jason Tumlinson has given me one of the longer talk titles I've ever been given. From Cosmic Birth to Living Earth, the next great space telescope beyond JWST. And for those of you who know, JWST stands for the James Webb Space Telescope, and that's not launching till 2018. Well, Jason isn't satisfied with just looking forward a few years. He's going to look even beyond that to the telescopes that will come after the Webb telescope. On March 3rd, we have a very special event for you. We have teamed with the Baltimore Museum of Art, and they have a guest artist coming in, Dario Robleto. And in his exhibit, he has several works inspired by Hubble. And he will come and chat with some folks from here about the interplay of science and art on March 3rd. So that will be a lot of fun. If you want to find out things on our webpage, we have this Go link up here. But as usual, it's easiest if you just use your favorite search engine, look for Hubble Public Talks, and you should find this webpage. We'll has a list of the upcoming lectures, information about other things, and also if you see this link down here, this is the archive to our lectures that have been webcast by our team here for the past decade. We started doing this archive just before Hubble's 15th anniversary, and so we are approaching our 10-year anniversary of webcasts. So you've got 10 years of cool talks to catch up on if you haven't been here before. By the way, I always like to ask every now and then, all right, how many people have not been here before? Wow, that's a larger proportion than usual. I guess the 25th anniversary got your attention? Cool, great. Love to have that. Email, if you would like announcements. We have a email list that like twice a month sends you an email reminding you of the upcoming lectures. So far we've had a perfect record of no spam. Of course, now that this is being webcast, I know some hacker is going to go out there and find it and try and ruin that, but so far we're just fine. We have an email address, publiclecture@stsci.edu, which is the perfect place to send an email to sign up for these announcements, because we'll have your email return address and can add you to the list. You can also use this email for comments and or questions. Now, the one thing I don't know, oops, I'm sorry, we have our social media on Facebook and Twitter and Google Plus and Pinterest. And for me, I have my Facebook and Google Plus and Twitter if you are so into following people in that way. One thing I don't know is the observatory. As a gentleman, I did not get an email today telling me whether the observatory would be open tonight. Usually they are, so this is a big question mark. And as someone down the front row goes, it's really cold. But you know what? The cold nights, you get the best seeing, okay? This is one of the unfortunate things of being an astronomer. When it's cold and the air is still, you really get better seeing. So I will ask again at the end of the lecture if there is somebody here to take you across. Otherwise, you will be able to go home and have hot chocolate instead of going and freezing your tootsies off in the observatory dome. But anyways, thanks to the Maryland Space Grant Observatory for providing that every month. Okay, so this is the point in the talk where I go to my news from the universe for January 2015. And our top story for tonight is, what? Are you kidding? I'm doing the main talk and had no time to gather news stories. Which I think is pretty much self-explanatory. So we move on to our featured speaker. All right. Our featured speaker tonight is myself, Dr. Frank Summers. Since we have so many new people here tonight, I'll give a little bit of my history. I'm an astronomer who got his undergraduate degree at Virginia Tech, go Hokies, and his graduate degrees at University of California, Berkeley. I then did postdocs at Princeton and Columbia. While I was at Columbia, I also was working at the American Museum of Natural History in New York, and I switched to full-time public outreach then, one of the 3 curators that built the Rose Center for Earth and Space in New York, the home of the brand new Hayden Planetarium in 2000. After building the Rose Center, I moved down here to Baltimore, worked with Hubble, and have been here for almost 14 years. I'm in the Office of Public Outreach here, and I get to work on all things Hubble. It's really a great job. I get to work on the news stories, I get to work on the website, I work on formal education, doing teacher training and informal education with museums and planetariums. And one of my specialties that I've developed while here is scientific visualization, having worked on 3 IMAX films, most notably being writer, science advisor, and scientific visualization supervisor on IMAX Hubble 3D 5 years ago. So, ladies and gentlemen, me. You already applauded, so don't do it again. Okay. Thank you for that wonderful and very knowledgeable introduction. I have an impossible task. I'm going to try to cover 25 years of Hubble in one lecture. And as I was getting this together, I found all sorts of cool stuff that I can't include in this talk because I spent this afternoon just hiding slides because there's so much really cool stuff. So I want to say to those of you who have your favorite Hubble images, the astronomers who might be watching who have their favorite Hubble observation, probably because they were the PI on it, and those of you who have this idea in your mind of just something that was just really struck you, I may not include it in my talk tonight. Okay, I have not decided on the best Hubble images. I have not decided on the most scientifically important Hubble images. I have decided on a suite of imagery that tells a story, the story that I want to tell you about Hubble's 25 years. Okay? So with that apology out of the way, let's go for it. Now, of course, you can't do 25 years of Hubble without actually going back 70 years. 70 years to this man, Lyman Spitzer, and he was working at the Rand Corporation in 1946, and he wrote a white paper on the idea of a space telescope, the benefits to astronomy of having a space telescope. 1946, that was before we even had the space age. The space age didn't come until a decade later with the beach ball that was heard around the world, Sputnik, that orbited around and started the beginning of the space age. Well, Sputnik orbiting around the world had stimulated a mission of the creation of NASA in 1958. The National Aeronautics and Space Administration, this is their original logo. This is their current logo today, created in 1958. America gets into space. Well, very soon thereafter, at the very beginning of the space age, in 1962, This is the National Academy of Sciences building in Washington, D.C. It's just another, ceremonial building in D.C., but it has this wonderful statue of Einstein out front. So if your kids remember it, they went probably out and sat on Einstein's lap when they were there. But the National Academy of Sciences convened a panel on discussing the benefits of what they called at the time a large space telescope. Recommended that America should move forward on putting a large telescope into space. This, of course, ignited all sorts of ideas. Everybody has their wonderful ideas. And astronomers are great people, but I gotta say, astronomers tend to think that they're the smartest person in the room, so they tend to want to have their idea go forward. And this one want to have their idea go forward. There's lots and lots of various ideas, various competing ideas, and not just in the US, but around the world. Well, the logjam was broken in 1976 when NASA, which by now had moved on to this wonderful worm logo, and ESA, the European Space Administration, decided they were going to do a joint proposal together. They pooled their ideas together, and that is what broke the logjam. That's what enabled enough political will to get Congress to fund the Large Space Telescope in 1977. Well, now that you've got funding and a plan, and it moves forward very quickly. In the 1980s, the telescope was built. In 1985, it was completed and construction. Here it is in Sunnyvale, California. And what is happening is it's undergoing a shake test here. Here's the guy in the bunny suit for scale. So this is a human size, and this is the size of the Hubble Space Telescope. It was certified for launch, and it was ready to go up on the space shuttle. Unfortunately, in 1986, we had the Challenger accident. The space shuttle program was grounded for several years, and Hubble sat in storage waiting to go up. Finally, in 1990, Hubble did launch. This is the launch of the Hubble Space Telescope. You'll notice there's another shuttle on the launch pad here. They were doing some testing there. There's only a few times in the history of the shuttle program when there have been two shuttles on the launch pad. They were doing testing here while they launched Hubble here. Here is the wonderful astronaut team that put Hubble into space. You will notice this gentleman right here. Does anybody know who he is? That's Charlie Bolden, the current NASA administrator. He put Hubble into orbit. So we hope that made him fond of our telescope. Here is the telescope sitting in the shuttle payload bay. You will notice that it fits very nicely in the shuttle payload bay. And that is, of course, by design, simply because we couldn't make Hubble any larger than what would fit in the shuttle payload bay. Okay? Would we have liked an even larger telescope? Of course we would. We're astronomers, and bigger is better when it comes to mirrors and everything. But we had a limitation. It's always good to have limitations. Our limitation was the size of the shuttle payload bay. The shuttle payload bay also carried aboard an IMAX camera. And this IMAX camera got this amazing shot of Hubble being set into orbit on April 25th, 1990. So Hubble is finally up there from 1946 to 1990. That's all the precursor history to get Hubble launched. Well, what happens first? We get stories like this. NASA's 1.5 billion blunder. We've got Hubble with a character of Mr. Magoo, and even XKCD, which is a very geeky comic strip, said Edwin Hubble's car, objects in mirror are blurrier than they appear, or something like that. I can't quite read that. So, well, Hubble's mirror was ground to a very exact shape, but it was slightly off. Okay? Hubble, after all this precursor history, had a flaw. All right? And if the flaw was actually not in the grinding, but in the testing apparatus for the grinding. Because from what I understand, there were some pins that were supposed to drop down into slots on the testing apparatus, and one pin got hooked up a little bit, and so the testing apparatus was slightly out of shape. The testing apparatus was telling the mirror polishing to grind it to a very exact shape, but just slightly wrong. What did that mean in practice? Well, it meant that a star, which is supposed to be a point of light, ended up having all this scattered light around it. Okay? So Hubble wasn't doing what it was supposed to. But that does not mean it was the Mr. Magoo of telescopes, okay? All of those cartoons, all of the things on Johnny Carson at the time overstated it, because Hubble could still do better things than we could do from the ground. For example, this is an image of a double star from the ground. And any astronomer who looks at that will tell you, yeah, that's a double star. Why? Because if it were a single star, it would be a circle. It is an oval, so there must be two sources in there to create that oval shape. Hubble, with the flaw, could see it like that. Okay? Now, those stars aren't perfect pinpoints of light like what we like them to, but we can still do science with the flaw in Hubble's mirror. So, what did we do? Here's another example. From the ground, this is what Pluto and Charon looked like. By the way, you got to remember that Charon had only been discovered in the 1980s. Okay? Many people don't remember that. Charon was only discovered in the 1980s. This was brand new. From the ground, you can see there's Pluto and there's Charon. With Hubble, you can easily distinguish them very clearly. You can still do things that are not capable from the ground. We can also watch other things, okay? So some of the science stories, in 1991, there was a major storm on Saturn. Now, we're used to having Jupiter having lots of storms. We know about the Great Red Spot and all the storms on Jupiter. But this is Saturn, and it only has storms like this in decades-long cycles. Matter of fact, they tell me the large storm before this was in 1933. So having Hubble up there to be able to see it was absolutely amazing. This is a storm that actually stretched all the way around the planet. 1991 also showed off Hubble's ability to use fine resolution to look into star clusters called globular clusters. Now, in this ground-based image here, you can see that the core of the globular cluster, this globular cluster called 47 Tucanae, is basically blown out. Usually, it is so dense in the cores of these clusters that from the ground, all the stars in the center are smeared together. Hubble, with its fine resolution, can resolve the individual stars. And what it found was a population of stars we call blue stragglers. Stars that, because of their age, should appear much redder, but for some reason they appeared bluer, which is younger than they should have, indicating that there probably were stellar collisions going on in globular clusters. Now, stars are just so far apart, they never come anywhere near each other, except in the incredibly dense environments of these globular clusters, showing that you can actually get two stars colliding in the cores of globular clusters. 1992, we looked at this galaxy, Messier 87. And Messier 87 is a giant elliptical galaxy in the center of the Virgo cluster. And you can see that it has a bright source in the center. This is a supermassive black hole. A supermassive black hole with approximately 1 billion times the mass of our sun. And it's outputting an energetic jet streaming across interstellar space. And the details of this jet were revealed by Hubble in 1992 in ways that you could not see from the ground. I'm hammering home that we can still do good science in those first 3 years. We did do great science in those first 3 years. Also in 1993, amazing thing that I only fully appreciated when I studied for this talk, looking at the Andromeda Galaxy. In the core of the Andromeda Galaxy, if you look way down in the core, you can see the center of Andromeda. Except for from the ground, you are fooled. That is not the core of Andromeda. When we studied it with Hubble, we could see that there are actually 2 cores in the Andromeda Galaxy. And what we had previously thought was the core of Andromeda is really a star cluster near the center of Andromeda. And the center of Andromeda is actually this lighter spot over here on the right. With Hubble's resolution, we're able to see into the core of that galaxy and find where the, actually, we expect a supermassive black hole will be in the core of that galaxy. Hubble did a lot of work in its early years studying the centers of galaxies, looking for telltale evidence of these supermassive black holes. And basically the answer is we found a supermassive black hole in every large galaxy that we looked at. Also in 1993, we had this wonderful image of a comet. This is comet Shoemaker-Levy 9, which was discovered in 1993, and it was in orbit around Jupiter, and it had broken up into many different pieces. The prediction was that Shoemaker-Levy 9 was going to strike Jupiter. But first, Hubble got its repair mission. Late 1993, this group of astronauts went up on the space shuttle to service Hubble. What they did is they added in glasses to correct the flaw in the mirror. Now, optics, there are a lot of things in life where we say, oh, it's not really an exact science. Well, optics really is an exact science. So we knew the shape that Hubble's mirror had been ground to, and we knew the shape we really wanted, so we could design an exact corrector plate to put in the pathway, think of it as some eyeglasses, to correct for that. Now, we put in an instrument called COSTAR, Corrective Optics Space Telescope Axial Replacement. Quite a convoluted acronym, but it worked, to correct the optics for the instruments that were already installed. And this here is Wide Field Planetary Camera 1 that's being taken out, and we put in Wide Field Planetary Camera 2, which had the correction already applied, so it didn't need any eyeglasses. Now you got to recognize that when we're looking at these wavelengths, we're trying to get down to a tenth at least of a wavelength, maybe even a hundredth of a wavelength. We're talking 10 nanometer scales that you have to position these optics. And frankly, I'm not an engineer. I'm not an optical guy. I was kind of unsure as to whether this would really work. Well, it did. Here is the view of a star before COSTAR was installed, and after COSTAR, boom. They did it, okay? I wasn't here at Hubble at the time, but they really nailed it. They got that point of light of the star that was expected. Hubble met its design specification and now could start doing the science it was intended. In particular, the imagery. The imagery is what really is going to attract your attention. Here is the core of the galaxy M100 from WIF-PIC 1. When we add in the new one, boom. Quite a difference. Now Hubble is up to its full capability. We can go back to looking at Comet Shoemaker-Levy 9. This is an image of those pieces of Comet Shoemaker-Levy 9 in 1994 with the repaired instruments, and you can see it's much clearer, but what we really wanted to see was it was going to smash into Jupiter. Now, let's think about it. These comet pieces are like 1 or maybe 2 kilometers across. Jupiter is 140,000 kilometers across. 2 kilometers? 140,000 kilometers. It's a pinprick, right? Nothing's going to happen. There was all sorts of debate, but fortunately, Hubble was looking because something did happen. And here's what Hubble saw in visible light. This is Jupiter, and you see these black marks? These are the impact sites, where these fragments of comets smashed into Jupiter's atmosphere and basically exploded and created huge holes in Jupiter's atmosphere. Every telescope in the world was watching, but only Hubble was above Earth's atmosphere and could also watch in ultraviolet light, where you can see the impact sites much more clearly. By the way, this is not an impact site, that's just a shadow of a moon, okay? One of the Galilean moons. So you could, and ultraviolet light, I know you all think that when you go out in the summer, you have to put on the suntan lotion because lots of ultraviolet light is coming down. Almost no ultraviolet light gets through our atmosphere in reality, okay? To do ultraviolet astronomy, you need a space telescope. That's why repair of Hubble, allowing it to get these amazing images, was ultra fortuitous in terms of seeing the observations of Comet Shoemaker-Levy 9. 1995, and right out of the gate, we're going to hit one of our best images ever. This is the so-called pillars of creation, the pillars in the Eagle Nebula. And to this day, it is one of our most popular images, if not the most popular. I gotta say, the public just loves ionization fronts, okay? What is an ionization front, you ask? Well, I'll answer that. So up there, a couple floors above us, there are some really, really bright stars. And they have high energy radiation and stellar winds streaming away from them. That energy is coming down like this, hitting these dense regions at the tops of the pillars, and you can see the bright light around them as it takes that dark gas, dense gas, this molecular gas, and ionizes it. The energy is transferred to that dark gas, and it ionizes. And you create these pillars because the winds are streaming down, and in here, it's not necessarily dense gas. It is just in the shadow of these dense regions at the tops of the pillars, and creates this great silhouette, this great contrast against the background of the image of the nebula. Also in 1995, as a matter of fact, 2 weeks after that image was released, another of our amazing images was released, this one of the trapezium region in the Orion Nebula, the center of the Orion Nebula, another star-forming region. And in the Orion Nebula, there are thousands of new stars being born. And plus, the center stars in here are also blowing off their winds, such that this object down here, LL Orionis, you can see has a bow shock around it. The wind coming down from these bright stars creates a bow shock around it. Right close to the trapezium stars, you can see that the bow shock is wrapped around to make a tadpole. All right? This is the wind streaming past the material around this forming star, creating a sort of windsock effect. And what's really cool is that if you look in detail, you can see these dust disks around brand new stars. And these dusty disks are where the planets are forming in a new solar system. Within the Orion Nebula, we get to see other solar systems in formation. And Hubble was the first to be able to give us the kind of resolution to see this amazing detail here. 1996, we go from star birth to star death. This is the star Eta Carina, and it is a 100 solar mass star, maybe 150 solar mass star, and it is not just being born, but instead we believe it's on its way to die. This is what we consider to be a pre-supernova star, a star at the end of its life that we expect to explode sometime in the next few million years. But what we can see here is an amazing detail of what's called the homunculus, these big lobes, these bubbles, the stars in the center here, and you can see this incredible bubble being blown from both directions, these bipolar bubbles, as an outburst from Eta Car going out, and again, detail that we had never seen before. We also, in seeing amazing detail, measured the first size of a star. Now, you may think about this. All right, well, we can see the sun, and it's a half a degree across. Okay, so we can see the size of that star. But every other star is so far away, it appears as a point of light even in our best telescopes. Well, with Hubble, we're able to make out the size of Betelgeuse. This is the shoulder of Orion here. It is a red supergiant star that is so large that if it were in our solar system, it would be larger than Earth's orbit. It would be larger than Jupiter's orbit. Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter would all be orbiting inside Betelgeuse, where our sun is. And with Hubble, we're able to measure the size of that star, the first one ever. Well, 1997 brought Servicing Mission 2, and this is the amazing crew that went up to service Hubble on the second servicing mission. Servicing Mission 2 added in 2 new instruments, the Near-Infrared Camera Multi-Object Spectrograph, otherwise known as NICMOS, which added to the infrared capabilities of Hubble, and the Space Telescope Imaging Spectrograph, which both of them are spectrographs, but they also add to STIS adds to the ultraviolet capabilities of Hubble. That mission, again, was a success. And this may look to you like a picture of Mars. It's not. This is something I discovered actually this morning as I was going through making sure I had all the really cool images. This is one I didn't know about. This is not Mars. This is Jupiter's moon, Io. And what you see on the limb of Jupiter's moon looks like a blurry thing, which is just an error, right? No, it's not. Jupiter's moon, Io, is the most volcanic object in the solar system. There are an average of 7 volcanoes going off at any one time, and the volcanic plumes reach so high they can actually be seen off the limb of Io. And I did not know until today that Hubble actually was able to see a volcanic plume on Io from Earth. I got to say, this compares very well to the New Horizons mission, and one of my favorite images in all of astronomy. This is the volcano Tavashtar on Io, captured by the New Horizons mission as it was getting a gravity assist flying by Jupiter. So this is an in situ at Jupiter image, whereas Hubble was able to actually see a plume as well being here at Earth. And I've been working with Hubble for 13 years, and that sort of surprised me that they were able to get that kind of observation. In 1997, we also looked at a favorite pair of galaxies for astronomers called the antennae galaxies. And you might be able to understand why they were called the antennae, because they have these big, long plumes sticking out from these twin centers. Well, looking at it with Hubble, these are 2 galaxies that are colliding. All right? And with Hubble, we're able to look into the detail into the core of this, and you see all these blue star clusters revealing the intense star formation that happens when galaxies collide. And in particular, what Hubble was able to discover was, with its resolution, it was able to see that these are not just star clusters, but what the astronomer called superstar clusters, very, very large clusters of stars that are formed when galaxies collide. Seen in the resolution Hubble looked at the antennae galaxies in 1997. 1998 flexed its muscle using the ultraviolet in STIS. This is Saturn, and you can see the aurora here on Saturn, both in the south and up in the north. Now, Saturn has aurora like Earth does, the northern lights and the southern lights, the aurora borealis and the aurora australis. However, Saturn's aurora is not visible is not seen in visible light. It is only seen in ultraviolet light. So again, you need a space telescope, and the ultraviolet capabilities on Hubble were improved by a factor of 10 with the addition of STIS, enabling us to see amazing detail in the aurora on Saturn, but also, by the way, the aurora on Jupiter, also visible in ultraviolet light. In the infrared, we looked toward Uranus. Now, if you've seen any pictures of Uranus, it's pretty boring. It's a pretty blasé, nothing of a planet. That's viewing it using visible light. In infrared light, we were actually able to see storms on Uranus. We're able to get the highlights of the rings around Uranus and several of its moons, transforming Uranus from a rather bland greenish planet to something with a lot more structure, seeing a lot more detail in the atmosphere of Uranus. 1998 is also notable because it was the start of the Hubble Heritage Project. All right? Hubble Heritage Project is a project to go through the Hubble archive and find the best Hubble images that haven't been released because of press. Not all the pretty pictures have good press, have great science that they're worthy of a press release. There's a lot of really cool stuff in the Hubble archive, and this project was started to go back and find those, and in fact has blossomed into a major source of really cool Hubble images, such that they often get some time assigned to them in order to take really cool images for special releases, including our Hubble 25th anniversary image, which I'll show you later. Now, Edwin Hubble was had 2 major scientific accomplishments that people associate with him. One is this observation of the Andromeda Galaxy, and really not the, and he was looking, these ends here indicate novae. Okay, he was looking for stars that would flash. He was looking for novae in the Andromeda galaxy. But he found this one up here and actually found that it was a variable star. And variable stars are special, at least the Cepheid variable stars are special in that the period of their variability, the amount of time it takes them to brighten and dim and brighten again, is related to their absolute brightness. And if you know their absolute brightness and you can compare it to the apparent brightness, you can calculate distances. And Hubble's second major discovery was that the distances to various galaxies were proportional to their redshift. Now, the redshift is a measure of their apparent motion away from the Milky Way. All right? When we look out into space, we see that all galaxies appear to be receding from us. And you interpret this as the expansion of the universe. So these are Hubble's great observations. But you know what? Edwin Hubble didn't have a Hubble Space Telescope. So he actually got the slope of this line pretty wrong. He actually used the wrong type of Cepheid variable and got his numbers kind of, well, they had a lot of error in them. Okay, but for the time, they were great. But we have the Hubble, and one of the key projects for the Hubble Space Telescope was to nail down, tighten up the expansion rate of the universe. Because at the time of Hubble's launch, there was a camp that said, no, the universe is expanding at 50 kilometers per second per megaparsec. You don't need to know what that means, just you know that this was the 50 camp. Then there was another camp that said it was at 100 kilometers per megaparsec, okay? Kilometers per second per megaparsec. And they were off by a factor of 2, right? And each of them had really good reasons for believing them. So what we did with Hubble is we used those same Cepheid variables, and we measured those Cepheid variables to all of as many local galaxies as we could using Hubble's resolution. Then, of course, measured the redshifts for them and recalibrated a brand new Hubble diagram. And this is a project that could not proceed during the first 3 years. Basically, you needed the exquisite resolution that Hubble had after servicing mission 1 in order to proceed this. So it took longer than we expected. But after 8 years of hard work in measuring the distances to 18 different galaxies in the local area, the HST Key project on the Hubble constant finally released their result, saying that the average in the local universe was a value of 70 plus or minus 10%. And I know that doesn't sound like much, but for astronomers who are used to a factor of 2, to get it down to 10% was amazing. This was the beginning of our precision cosmology, when our cosmological models, which when I was in graduate school were wildly variable, and you could take a lot of different parameters and still fit the data. Finally, we start getting precision. We follow it up with the cosmic microwave background observations and such. And over the course of Hubble's lifetime, we have gone from a lot of uncertainty in our models down to a very tightly fit model. This is one of the key points in that transition. Another really cool thing that caught my eye, I wasn't at Hubble at the time, I was up in New York, was this image right here, HR 4796A. Now, what this is an image where the light from the star has been blocked by an occulting spot, okay? It's like when you're looking at the sun and you're going, oh, I want to block that, right? Well, that's all we do in astronomy. We block the light of the star in order to see the faint material around it. And this is, on the scale of the distance to that star, the diameter of Neptune's orbit. We had in the 1990s just begun to discover the Kuiper belt in our own solar system. And when we saw 4796A, we pointed at that and said, damn, that looks like we're seeing a Kuiper belt in another solar system, around another star. Starting to see anything. And in this one, HD 141569, you see rings, but you also see a gap. And gaps are really important because the only way a gap opens up is if there's a gravitational force pulling to create that gap. It doesn't mean that there's a planet inside the gap. There could be. But there could also be a planet inside or outside that gravitational resonance is opening up that gap. we're beginning to not only see planetary systems in formation, but to start to see some of the details of planetary systems. Well, 1999 ended on a sour note. In November of 1999, we lost our 4th gyro. Now, Hubble has 6 gyroscopes on it, and it needs 3 gyroscopes to point. You've got 3 directions, X, Y, and Z, and you need 3 gyroscopes to work with each other to point the telescope accurately. Well, our 4th gyroscope failed in November of 1999. Hubble was put into safe mode, and Hubble could not do any more observations until the astronauts went up to repair it. How long was that going to take? Not long. NASA came to the rescue, and in December 1999, they put a Hubble servicing mission onto the shuttle manifest very quickly, servicing mission 3A. Now, it's called 3A because we had a much larger servicing mission plan, full servicing mission 3, but because Hubble needed hardware repairs, they took the hardware repairs only and pushed it up in the schedule, got up to Hubble almost immediately, did the hardware repairs, replaced the gyroscopes, topped off the fluids, washed the windshield, replaced the recorders, put on outer blanket layers, insulation, stuff like that. Okay, didn't add any new capability to Hubble, but repaired it and got it back into working order. Now, of course, when you have a successful servicing mission, you have to announce it with some beautiful images. And in 2000, we announced it with this. This was one of the images we used to announce it. This is the galaxy cluster Abell 2218. This is a galaxy cluster with thousands of galaxies. And the mass concentration in this globular cluster, in this galaxy cluster, is so great that it actually warps space. Now, general relativity, for those of you who come often, there's a 3-word summary of general relativity. Anybody remember it? Mass warps space. Everybody say it with me. Mass warps space. That's all you need to know about general relativity. All right? And there's so much mass in this galaxy cluster that the space has become warped. And these arcy, streaky things that you see around this galaxy cluster are images of galaxies behind the cluster whose light has come through this warped space and become stretched out while passing through that warped space. They're normal-looking galaxies, but the images have become distorted by passing through distorted space. How cool is that? And you will note how thin and detailed you have to look in order to see these gravitational lenses, these gravitationally lensed arcs. And Hubble's resolution has enabled greater studies of gravitational lensing than was ever possible before. Seeing that amazing detail, these fine, detailed structures, possible with Hubble and gravitational lensing, it has really greatly pushed forward that field. 2001, we returned to the solar system, and Mars makes periodic approaches by Earth. Okay? Earth is orbiting around a little faster than Mars. Mars takes a little bit longer. Every 2.5 years, they go into what's called conjunction. Earth and Mars are at their closest approach. Okay? Hubble always takes pictures of Mars. Why? Because the public loves the solar system. All right? Cosmology is great. Those gravitational lenses, things are fantastic. But you know what? The public responds to a solar system press release more than anything else. Also, it's a really good time to study Mars, and we've got the best resolution that you can have from Earth. Now, of course, the resolution is nothing compared to the spacecraft that are there at Mars. We can't compete with that. But, we can do some things. One of the things we can do is we can monitor it long term. See, in June of 2001, here's the picture of Mars, and you see that's the Hellas Basin down there. And there was a dust storm brewing in the Hellas Basin. Okay, a giant impact crater on Mars. You've got a dust storm brewing. And so we watched it, and we looked in September. Oh no, is the flaw in the mirror back? No. The dust storm that was a localized disturbance in June has gone global in September. Mars's atmosphere is 1/100th the density of Earth's atmosphere, and localized disturbances can propagate to become global phenomena. That's what happened here. Hubble gets to monitor the planets over the course of decades. When you send a spacecraft to a planet, it's there for a few years. You know, Cassini has done absolutely amazing being there as long as it has been. But Hubble is around there for decades, and sometimes I like to refer to Hubble as the Interplanetary Weather Channel because it can monitor what's going on in these planets from here at Earth over long term. 2001 also saw an amazing discovery. This is the Hubble Deep Field that was done in 1995. And in that are this galaxies here, this small suite of galaxies here. And in this galaxy here, we observed a supernova. This galaxy is, however, 10 billion light years away, making this the most distant supernova ever observed. Now, what you're seeing in the lower right-hand panel is basically two images of these galaxies subtracted to show you the light remaining, that extra light that came from that supernova. Now, what's really cool about this is that this supernova, being so far away, being able to give us the distance to that galaxy and compare it to its redshift, like we did with the Hubble diagram, was able to nail down our cosmological model. As you may be aware, in the late 1990s, we had evidence that the universe was accelerating. The expansion of the universe, instead of slowing down like we'd always thought it would, appears to be going faster. But we couldn't really tell unless we looked way, way out in the universe. Our confidence locally was very strong. But unless we looked way, way out in the universe to see back when the universe was slowing down, could we truly tell? This galaxy, this supernova, at a redshift of 1.7, the most distant supernova ever observed, was a crucial point in accepting the accelerating universe and the discovery of dark energy, the kind of thing only observable with Hubble. 2002, we got the second half of Servicing Mission 3, Servicing Mission 3B, and again, the wonderful astronauts who went up and serviced it. Now, Servicing Mission 3B was especially cool because we had, for the first time, a major change of our primary observing instrument. We had been using Wide Field Planetary Camera 2 since 1993, which was installed in Servicing Mission 1. And in this servicing mission, we installed the advanced camera for surveys, going from a 3 megapixel camera to a 16 megapixel camera, going from 1/10 of an arcsecond resolution to 1/20th of an arcsecond resolution. So slightly larger field of view, higher resolution, more pixels. Really exciting. We also, during this mission, I'll have to say, there was a power unit repair. And I have to say that one of the most dramatic lines I've heard at NASA, we know the NASA guys who are narrating these things, and they're very calm and very professional. He said something like, you know, that when they disconnected the power unit in order to do the repair, he said, for the first time, Hubble is without a heartbeat. It was like, whoa! Fortunately, Hubble did recover from open heart surgery and to go on and do amazing things. With our early release observations, we included this image of the mice galaxies, which looks a bit like the antennae, but it's now at Hubble resolution. That antennae image I showed you was from the ground. Here you get to see all the detail as well as those big, long tidal tails. And the mice were part of our press release to say, Hubble is back and working. Perhaps the most successful press release we've ever done because we got 1, 2, 3, 4 Hubble images on the front page of the New York Times in full color above the fold. A grand slam of public outreach, if ever there was one. I don't know how we could possibly do any better than that. So, but we have tried for the past 13 years. All right. 2003, that advanced camera for surveys puts its 16 megapixels to use, and we start doing mosaics. This is a mosaic of 72 million pixels of the Sombrero Galaxy. And it's a gorgeous galaxy with its amazing dust disk and the big halo of stars, but also you'll find that the background galaxies, all the details in the background, ACS is that much more sensitive that it's not just the foreground objects, but we find ourselves starting looking through the background objects. We're seeing amazing detail in the background of all our images as well. We also took a very deep look at a nothing part near the Andromeda Galaxy. So this is the region that we studied, well away from the center of the Andromeda Galaxy. In the halo of the Andromeda Galaxy, we did what we call the stellar deep field. And this is an image in which almost all the stars you see are not in our galaxy. Almost all the stars you see are in the Andromeda Galaxy. This is an amazingly deep image to study the stellar populations within the Andromeda Galaxy. For example, okay, by the way, these also are background galaxies. We can't get rid of them, okay? They're going to be in the background at all times. But see this guy right here? That is a globular cluster, not in our galaxy, but in the Andromeda Galaxy. And for comparison, I give you a globular cluster in our own galaxy, also taken with Hubble. Messier 80 in the Milky Way, and I guess, what is it, G1 or something like that in Andromeda. Absolutely amazing that we can get this detail from a galaxy 2.5 million light years away. Unfortunately, this is a shot of the astronauts at the landing of the Space Shuttle Columbia after servicing Mission 3. And unfortunately, this was the last successful mission of the Space Shuttle Columbia. On its next mission, it disintegrated as it was coming in over Texas. And this gentleman right here, Sean O'Keefe, was the then NASA administrator. And in January of 2004, he decided that it was too dangerous to go back to Hubble, that there was no safe haven for the astronauts. If they were going to the space station, well, the astronauts could hang out on the space station if there was a problem with the shuttle until a rescue mission could be sent up. But Hubble, there was no safe haven. So in January 2004, he announced the cancellation of our last servicing mission. Servicing mission 4 would be no more. I cannot describe the, I don't want to say depression, but the general around this building at the time. All right, we'd been through so much in getting, and Hubble has triumphed, but to not have that last servicing mission, well, that was quite a blow. We'd already started building the instruments for it. Okay, but that doesn't mean that the science stops. So this is an image released in 1994 looking at supernova 1987A. Now 87A is the closest supernova since the invention of the telescope. It's actually in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. We've been very unlucky for the past 400 years. We haven't had a good supernova in our own galaxy. But 87A exploded, we observed the explosion in 1987, and this was the Hubble image in 1994. And you can see here is the star that exploded here. You can see there's a ring here and these two amazing rings here, indicating that before the star exploded, there was some outbursts of material to create these rings. Whether it was jets illuminating this, rotating jets that would illuminate these rings, you have this ring of material here. Well, we've been following it ever since. Okay, the closest supernova, you betcha Hubble's going to follow it. And in 2004, we released this amazing series of images of that central ring. So here is that ring. This bright spot here is just a star that happens to be along the line of sight. So you can ignore that. But as we go through 95, 96 to 98, you start to see other bright spots lighting up along the ring. You'll also notice this central region becoming blurrier and bigger until in 2003 you can see the entire ring is basically lit up, and this is the supernova remnant. what's happening here is the star explodes and a shock wave is sent out at tens of millions of miles an hour across interstellar space. What you're seeing here is that shock wave encountering that inner ring and heating up that inner ring. We're seeing in real time the shock wave smashing into this ring, creating all these bright regions. Plus, we are seeing the gas of the supernova remnant expand out in real time. We've been following this ever since. It's absolutely amazing. Not too many things in astronomy happen in real time, and Hubble has been there to be able to monitor the expansion of supernova 87A. Now, also in 1996, we did the Hubble Deep Field. I mentioned it previously. This was quite a risky observation. Basically, the director at the time put all his discretionary time into one observation. And it's an observation that a lot of astronomers said would totally fail, because distant galaxies, if you believe some models, were predicted to be too small for even Hubble to see. That as you go further out, the galaxy's smaller and smaller, you're not going to be able to see anything. But he put all his eggs in one basket and produced this amazing image, the Hubble Deep Field, showing that you really could do deep universe observations with Hubble, that Hubble's resolution was good enough. Well, we got the advanced camera for surveys. The new director said, I got to repeat this with our new instrument with twice the resolution and many times the pixels. And so in 2004, we also came out with the Hubble Ultra Deep Field. Okay? And this is probably the most scientifically productive image Hubble has ever created. All right? It has approximately 10,000 galaxies all the way stretched across space and time, looking way out into the universe from our big nearby galaxies. And when I say nearby, I know that that galaxy is about 2 billion light years away, so that's nearby in this image. Just a couple billion light years away is nearby. All the way down to, I don't know if I can pick out one of the red dots. There's a bunch of little red, tiny red dots. You probably can't see it at this resolution. Tiny, tiny red dots stretching out 10 billion light years across the universe. A core sample through the universe looking at galaxies out in space, but also back in time. Because this galaxy being 2 billion light years away, the light has taken 2 billion years to cross the intervening space. So we're seeing this galaxy as it was 2 billion years ago. This image looks out into space, back into time, and shows us the history of galaxy development across the universe. You know, a history teacher can't look out and see the Battle of Gettysburg, but we as astronomers can look out and see what galaxies were like billions of years ago to give us an understanding of how galaxies developed to be the way they are today. Unfortunately, in early 2005, the advanced camera for surveys, its warranty obviously expired, and it had an electrical fault. Okay, all of our instruments on Hubble have redundant electronics. The one side of the electronics had failed previously. The second side of the electronics failed. Our main instrument, the instrument that took that Hubble Ultra Deep Field image, was now offline. Here it is, 2005, and what are we going to do? We're going to go back to the white. Oh, I'm sorry. This isn't ACS. This is STIS. STIS failed in 2005. ACS will fail a little later. Sorry about that. Oh, I've blown it. The surprise is gone. Okay. The Space Telescope Imaging Spectrograph failed first. I'm sorry. I should know because the picture of ACS actually says ACS on it. All right. This is not them trying to repair it. This is actually as they were building the STIS instrument. Okay. Not to get anybody to think that we actually could go up and do this kind of repair. So we were without STIS. 2005, our 15th anniversary, we released this amazing image of the Whirlpool Galaxy, also known as Messier 51. 96 million pixels of visual goodness here. What I love about this image is that you can see the progression of star formation within a galaxy. You've got the dark dust lanes that identify the spiral arms, that trace the spiral arms. Outside of them, you've got all these pink regions. These are the star-forming regions where that dense gas in the dust collapses and creates new stars. And then outside of those pink regions, you see these wonderful blue star clusters, the newborn stars, going from the dense gas that collapses to the stars that form to the star clusters that are revealed when that star formation is done. Also in 2005, we got this amazing picture of the Crab Nebula. This is a supernova not 10 or 20 years after it had exploded, but 1,000 years after it exploded. This supernova was observed by Chinese astronomers in 1054, I believe, about 1,000 years ago. And all that material streaming across space, you saw that little nebula starting to form in the center of a supernova 87A. This is what it looks like 1,000 years later for the Crab Nebula. If you want to take a look at one that's 30,000 years old, we also got a picture of Cassiopeia A in 2006, an older supernova remnant that has expanded across space for 30,000 years, leaving a beautiful bubble, this bubble-like shell, the star that exploded, long gone, and seeing the shell of material. And this exemplifies the cosmic recycling in our galaxy, that the elements form inside stars. You fuse hydrogen to helium, helium to carbon, nitrogen, oxygen, and so on up the ladder. And then with these giant supernova explosions, those elements are blown across space and recycled into the interstellar medium. And in some pockets of those interstellar medium, stars will form, and around some of those stars, planets will form. And the heavy elements, which can only form inside these stars, form to create all the carbon in your, the oxygen in your lungs, the calcium in your teeth, the carbon in our bones. All of those elements were forged in the interiors of stars and blown across space by these supernova remnants. So there's a great cosmic connection to images like this. 2006 also produced one of my favorite images, simply because we got to work with it on the IMAX film, of the Orion Nebula. Now, I showed you the 1995 version of Orion. That was a relatively small region in here. This one is much larger. Actually, it was so large that we couldn't, with the computers of the time, process the entire image. What you'll find on our website is about a 320 million pixel image. The full one, had we been able to process it at full resolution and release it, would have been about 1 billion pixels, which for the computers of the time was not feasible. But again, even more detail of the amazing star formation going on inside this nearest of the large star forming regions to us. Good news. 2006 also saw we had a new NASA administrator, Michael Griffin. He came on a couple years before this, and he commissioned a study to look at servicing mission, possibility of a servicing mission 4. And in the middle of the year, he added a servicing mission 4 back onto the manifest. But in order to protect the astronauts, it was decreed that you could not do a Hubble servicing mission unless there was a second shuttle on the launch pad ready to go in case a rescue mission was needed. So that was our solution. If you're going to go to Hubble, you need 2 shuttles on the launch pad at the same time. Of course, that had happened before at Hubble's launch, so we're going to do it again. As we might say, the mood around this building really lightened after that. Much jubilance after that. However, this is when ACS, now you can see it is ACS because there it is, ACS failed. All right, so again, we're without the Space Telescope Imaging Spectrograph, we're without the Advanced Camera Surveys. 2 of our really important instruments are no longer working. We really, really want that servicing mission to come as soon as possible, but it was scheduled for 2008. So we got lots of science to go through. 2007, this is an artist illustration of a planet around a star, and in a Jupiter-sized planet in a Mercury-sized orbit. We call them hot Jupiters. But this one actually passes in front of the star from our point of view, which makes it really cool. Well, actually, it's really hot, but really cool to study, because you can see as that planet passes in front of its star, some of the light of the star will go through the atmosphere of this star. And this star is this planet is so close to its star that its atmosphere is actually heated up and extended. So if you take a picture or a spectrograph when the planet is in front of the star, and take another when the planet is not in front of the star, subtract the two, what do you get? You get to measure the atmosphere of a planet around another star. Now, you can't actually see this planet, but you can measure its atmosphere. And this atmosphere is extended, and we're able to measure hydrogen and silicon and nitrogen and a couple other elements in the atmosphere of another planet. And I have to say, this is one of the Hubble discoveries that we hadn't even dreamed of when Hubble was launched. One of the great things about science is that if you design a general purpose instrument, you can actually do science you didn't even think possible when you initially conceived of the idea. And this is one of the major ones. Also in 2007 we got, well, this was until last Monday, the largest mosaic Hubble has ever done. This is of the Carina Nebula, another star-forming region. That Eta Car image that I showed you is this small thing right here, down inside there. You can see it's just part of a much larger star-forming region. You can see there's an amazing bubble, a cavity, drawn by these bright stars and their hot winds and everything. And we've got the pillars here and pillars down here and all sorts of cool stuff going on in here. This 400 million pixel image shows off the incredible detail Hubble can see in these star-forming regions. 2008, well, let's get to Jupiter, because we talked about Jupiter's storms. We talked about Saturn's storms and how Jupiter is used to having storms. Well, we are used to one major storm always being there on Jupiter, and that is the Great Red Spot. We have seen it ever since we started looking at it. We have continuous observations back to the 1800s. We may even have seen it back in 1670 when Giovanni Cassini, he's got a wonderful drawing in a 1670 scientific journal, and I swear it looks like the Great Red Spot. So it's always been there, all right? In 2003, several of these white ovals merged to form what we called Red Spot Junior, the first time we'd ever seen the formation of a red spot. And in early 2008, another red spot appeared. This was the Great Red Spot, Red Junior, so we call that Baby Red Spot. Now, Red Junior is on a different latitude and has passed by the Great Red Spot several times and appears to be a long-lived storm. However, the Baby Red Spot is on the same latitude as Jupiter, and so we watched over the summer of 2008 as it got caught in the vortices and was dissipated. For the first time, we saw the destruction of a red spot. And we also learned how vicious the Great Red Spot is. It's such a vicious storm, it'll even eat its own young. 2008 also saw this wonderful image. This is Fomalhaut, or actually it's everything but the star Fomalhaut. Again, the light of Fomalhaut has been blocked, and it's got a dust ring around it. Looks similar to some of the images I've shown you before. But the special thing about this dust ring is that it's off-center. Fomalhaut is not at the center, which indicates that there's some gravitational influence pulling it off-center. So it was searched to see if we could find a planet in it. And in 2008, we saw the first image ever of a planet around another star. Right there. A beautiful red dot. But it's an amazing red dot when you think of it, because this is not a planet I'm telling you is there because of its gravity or because I detect it blocking some light. It's not an indirect detection. This is the first direct detection of a planet around another star. Now this is the one in visible light, using visible light in the exact same issue of the exact same scientific journal. Another group released images in infrared light. So starting in 2008, we finally have direct detection seeing planets around other stars. And you think about how far we've come over the first 18 years of Hubble, going from not even knowing there were planets around other stars to finally seeing them. You can see what a spectrum of science this mission has covered. 2008 was finally we get around to servicing mission 4. And a quote from a high-ranking person at NASA says, "This final mission will be, without doubt, the most complicated and challenging that NASA has ever mounted." So here we are in September of 2008. We have the space shuttle on the launch pad. We have the second space shuttle on the launch pad. There's a beautiful rainbow up here that I had to crop off to get the image in. Amazing shot. All right, we're ready to go. And then the Science Instrument Control and Data Handling Unit failed. Now, this was just the A side of the electronics of the SIC and DH. And there was a B side, so we immediately switched to the B side. But Science Instrument Control, this is the hardware that controls every science instrument on Hubble. Data Handling Unit, every bit of data goes through this piece of hardware. So when it failed 3 weeks before launch, and even though it was a repairable fail, we didn't want to have any single points of failure. So NASA delayed the mission, while a ground spare at Goddard Space Flight Center was made ready for space. So that mission that we'd been waiting for was delayed yet another 6 months until May of 2009, when we finally got the launch of Servicing Mission 4. Now, Servicing Mission 4 tackled an enormous number of tasks because it was the final mission to Hubble, and we knew we were not going to get another mission to Hubble. So we changed out the batteries. We put in new gyros. We pulled out Wide Field Planetary Camera 2. We put in Wide Field Camera 3. We repaired ACS. We repaired STIS. We put in new insulation. We did everything possible to leave Hubble in as good a shape as we could. And unbelievably, the astronauts accomplished it all. They went well past their space time, the time that they're supposed to do for spacewalks. They accomplished everything on the list. All right? And this is a bittersweet shot because this is Hubble repaired, but this is also the last time human eyes got to see Hubble. Because as the astronauts were leaving, this is one of the last shots they got, saying goodbye to Hubble. Of course, the science comes out amazing. The early release observations included the Butterfly Nebula. Actually, it's called the Bug Nebula, but our press release said it looked like a butterfly, and the press ran with it, so now most people call it the Butterfly Nebula. This is a dying star, a planetary nebula, as they call it, not because it has anything to do with planets, but that's just what they were called. And the material streaming away from the star is constrained by a disk around here, so it goes off in these hourglass shapes here, creating an amazing and beautiful nebula. We also released this image of the core of the globular cluster Omega Centauri. I talked to you about the detail Hubble can see inside globular clusters. This was not intended to be a press release image. It's a test image because the blue is ultraviolet, the red is infrared. This was a test image to show off the broad wavelength coverage of Wide Field Camera 3, the largest wavelength coverage of any instrument ever on Hubble, to show off, but it was such an amazing image that it ended up making its way into the press package. Both of those images were featured in the IMAX film, Hubble 3D, and my personal note on this was that when the servicing mission was delayed from October to May, the film's release date was not. And those of us working on the computer graphics for this film had to wait until after the servicing mission because the IMAX director couldn't pay any attention to doing the beautiful shots we were doing until after the servicing mission was done, and she'd gotten the footage from the servicing mission to put in the film. So that delay in the servicing mission actually meant we had 6 months less time to work on the computer graphics for the film, but we still accomplished it. It was really wonderful, but that delay hit me in a way that I'd never even expected would happen. But that film has grossed over $50 million worldwide, which is tremendous for a documentary. It's on track to become one of the top 5 IMAX documentary films of all time. 2010, for Hubble's 20th anniversary, released this image, which we nicknamed Mystic Mountain. And it is again pillars like the pillars in the Eel Nebula, but here you can see we've got these jets of material streaming off up here. These are what I call the birth announcements of a newborn star. When stars are born, they often have these twin pillars of jets streaming out. And you can see up not only here, but also here. Again, gorgeous ionization fronts, but this time with jets to show them off. 2011, the galaxy's ARP 273. Something that was nicknamed the Rose, because these two galaxies have been interacting, but only gently. And you can see that this galaxy has become stretched out and got a little bit of tidal tails up and down, whereas the spiral arms of this galaxy have become stretched out. And if you sort of squint at it, you can see this is the stem with the rose up at the top. 2011 also saw the awarding of the Nobel Prize in Physics to Adam Rees here at the Space Telescope Science Institute. And to be fair, it was awarded for the work he did on the accelerating universe before he was here. But as I mentioned before, because Hubble played a pivotal role in verifying and giving the scientific community trust that the accelerating universe was correct, we like to celebrate it too. He's also here. If you want to see a replica of the Nobel Prize, it's medal, it's out in the lobby, and you can see it as you go out. 2012, remember that Pluto-Charon picture I showed you at the very beginning from 1990? Well, we went beyond looking around Pluto for the New Horizons mission, which will get to Pluto in July of this year. We found not 1, not 2, not 3, but 4 other moons around Pluto and Charon, basically taking from 2 to 6 the number of targets the New Horizons mission has to look at. So the detail in Hubble with its new instruments able to see really fine and faint things out at the edge of our solar system. We can also see really fine and faint things out at the edge of the universe, but for that we're going to use a little bit of help, because I talked to you about gravitational lensing and how there's a lens in space. But we can use that lens to magnify really distant galaxies and see galaxies that Hubble could never otherwise see. These images, JD1, JD2, JD3, are all of the same galaxy whose light has been not just distorted, but also magnified so Hubble can see it. This is one of the most distant galaxy candidates ever discovered at almost 13 billion light years away. I never remember the numbers on those. It's like between 12 and 13. Okay? 2013, we start revisiting some images we had taken before. This is the famed Horsehead Nebula, which, in using visible light, has a great dark column. And there's not much to see it. There's not much detail in it. But with the new infrared capability of Wide Field Camera 3, we take this same image on a larger field and you get a glowing gaseous landscape in the infrared. All sorts of detail shows up when you look in the infrared and see the cooler gas and the structures that you can see in the Horsehead Nebula. We also revisited that Hubble Ultra Deep Field. We'd been revisiting it in the infrared in 2009, and so we were able to get further and deeper in the infrared. And in 2014, we said, let's extend that to the ultraviolet. Let's take advantage that we have ultraviolet, visible, and infrared, and together we produced the multi-wavelength ultra deep field in 2014, the deepest image of the universe covering a broad spectrum of colors. So based on all that, what are we going to do for the 25th anniversary? Well, for the 25th anniversary, we decided we would revisit a classic. We would go back to that Pillars of Creation from 1995. And you can see how it has that stair-step shape due to Wide Field Planetary Camera 2. We would go in with Wide Field Camera 3, look at it, and I present to you the 25th anniversary image, the new WIFC 3 image of the Pillars of Creation. You can see it covers a much larger field of view at greater detail, twice the resolution. There's approximately 60 million pixels of visual goodness for you to explore. You can see that those pillars fade out here, but yet new pillars are underneath. I sort of think of this as this looks like the tree stump underneath it. You can also see how the gas fades away as that streaming of it pulls the gas off. I had a friend at the AAS who said, oh, I know what that looks like. That looks like the Dementors from Harry Potter. All right, so this should be the Dementor pillar. But let's take it one step further, because we have with C3, it has broad wavelength coverage. We can look in the infrared. And in the infrared, we see that. I talked to you about how these pillars have these dense regions at the top, but aren't necessarily dense all the way down. Here you can truly see that they are not dense all the way down. If I go back to the visible light, you can see that the gas of the nebula obscures all the background. If we go to the infrared, all of those background stars start to appear. You can even see some background galaxies in through here. Take a look at these 4 bright stars there. Very bright in the infrared. But where are they in visible light? Okay? Looking in different wavelengths gives you a whole new perspective. This is why having multi-wavelength coverage is so important. Whoops. That's not me. There we go, we're back. Looking in multi-wavelength is so important to give you as many views and many ideas on the physics that's going forward. So, over its 25 years, Hubble has produced an amazing panoply of images. It has looked at planets and stars and nebulae and galaxies and all the way across the universe. But this is a scientific telescope, and the true measure of Hubble, of course, has to be the science. So here's a plot we made back in 2011 to celebrate the scientific publication, Hubble's scientific publication record. So we have the number of refereed science papers. Notice that these are refereed. These aren't just papers written, they have been refereed by other scientists. And over the course of its history, these are per year. Okay, we're getting up 600-700 papers. This plot was produced to celebrate the 10,000th refereed scientific paper. By today, we are over 12,000 refereed scientific papers. This is where you, as taxpayers, are getting the bang for your buck. Yes, you enjoy the pretty pictures, but the fact that we have changed science across all scales of astronomy with this many refereed papers is the true value of Hubble. So I'm going to finish with one of my favorite images of Hubble. It, to me, is hopeful. It is looking up, staring out at the universe, and it has that hopeful feeling to it. And you may think that after 25 years, Hubble is old. Hubble has been around, okay? It's on its downside. But I gotta tell you that while the instruments may be older, the telescope may be older, the scientists and the computer programmers and the ability to use the telescope has only gotten better. Our understanding of how to use the telescope to preserve the batteries, how to use the telescope to use the gyros. We can go down, if we lose 4 gyros, we can operate and do 95% of the science in 2 gyro mode. We've even figured out how to do 60% of the science in 1 gyro mode. Okay? Our scheduling has gone from approximately 2 months down to less than 2 weeks for utilizing the telescopes. We keep gaining efficiencies. And last year, 5 years after servicing Mission 4, when the warranty on servicing Mission 4 had run out, a top official in this building said, you know what? Hubble is actually at its greatest power now than it has ever been, because of the efficiencies we are learning in utilizing this telescope. So I have always said I want to see Hubble live to 2020. I want to have it still up and flying and actively observing when the James Webb Space Telescope is up. That would be fantastic. Then we could have 2 NASA's flagship missions observing, one with visible light, one in the infrared, to really pin down ideas. Because Webb will have Hubble resolution across the infrared spectrum. But you know what? I'm possibly starting to think that maybe we could go a bit further. Right? I started giving these retrospective talks at Hubble 15 back when Servicing Mission 4 was canceled. And I gave one at Hubble 20, and I'm giving it at Hubble 25. I hope to see you all here for Hubble 30. And dare I even think about Hubble 35? I don't know. I just have to say that I, in my years here, have been amazingly impressed with the dedication and the professionalism of the staff here. They do an amazing job. Hubble has transcended astronomy. I can say Hubble and the public knows what I'm talking about. You can't talk about a particle accelerator or a scanning electron microscope in the same way. All right? It is part of the public vernacular. So it has changed astronomy. It has changed our view and changed our understanding. And I hope you will join with us this year in celebrating its 25th anniversary, as I like to call it, a celestial silver celebration. Thank you for your attention. Okay, according to my own rules, I have 4 minutes for questions if you would like to ask any questions. Otherwise, I have to pull myself off stage. So do we have any questions that I can answer? I know I talked long, but I'm sorry. There's just so much cool stuff to show. Yes, right there.
Has Hubble ever pointed towards Earth? You have a couple of lights.
Has Hubble ever been pointed towards Earth? Hubble has an infinite focus. It's pointed out into the universe. The closest thing it's ever observed is the moon. Okay? Hubble would be useless pointed towards Earth. And besides, the other parts of the government have much better ones for doing that. Other questions? Yes, over here.
Also, the field image from 2004, you didn't see the gravitational lensing streaks, even with the previous wide field.
You're talking about the Hubble deep field did not see, there's no gravitational lensing in either the Hubble Deep Field or the Hubble Ultra Deep Field. If you thought you saw gravitational lensing in the Hubble Deep Field, it may have been an artifact of the process.
How come in one of the field images there was gravitational lensing, but in that
So you get gravitational lensing. So the question is, how come there is gravitational lensing in some images? You get gravitational lensing when you have a cluster of galaxies providing the mass to do the lensing. Okay, so the mass creates the lensing. The Hubble Deep Field and the Hubble Ultra Deep Field were chosen to look in regions where there would be no large clusters. Matter of fact, we tried to find the emptiest spots in the sky so that we could see as far into the universe as possible. We're trying to get rid of all the Milky Way stars, all the Milky Way gas, all of the known galaxies and clusters. So we didn't look in those regions. It actually is an exercise in trying to find the most boring part of the sky you can find. Yes, down here.
Is that for a servicing mission approved?
All right, so he starts out with it. If there's ever a servicing mission approved, we have no shuttle program, so there isn't a servicing mission approved. So go ahead.
I mean this is a theoretical.
Theoretical, okay.
But what do you think NASA or the Institute would do to actually improve the Hubble the way it is now? Would there be any further improvements?
Well, we are not working on any. All right, so the question is, could we improve Hubble if there was some possible chance? Say Elon Musk decided that he was going to go to Hubble, okay? By damned, he could do anything, right? We would have to develop instruments, and whoever would try and service it would have to develop an entire suite of servicing materials. I mean, Hubble was designed to be serviced in the shuttle cargo bay. It has the Lazy Susan there and all of the instrumentation and everything designed to work with Hubble. To recreate that would be well nigh impossible. So that's one thing. But in order to improve Hubble, we would have to be developing the repair parts or the new instruments, which are not being developed. And those take several years. People worked on ACS for 5 to 7 years before it launched. So it takes quite some time to do that. So it would have to be a concerted effort and would have a long lead time if such a thing were possible, but I don't believe it is. Yes?
What is the present plan for deorbiting if there's no way to get there?
The present plan for deorbiting Hubble is to have a robotic mission. During service in Mission 4, they installed on the bottom of Hubble something called the SCM, the soft capture mechanism, so that a robotic mission could go up and grapple with Hubble and then deorbit it safely.
Oh, the fixture's already there.
Yes, the fixture is already there on Hubble. Now, is there a mission plan to do that? No. Will all of us start crying if that happens? Yes. Is there much else we can do right now? No. Because we have to deorbit it safely, okay? After Space Lab in the 1970s, we learned our lesson. We're not going to let things come in an uncontrolled deorbit, right? So if we can't find some way to do something else with Hubble, it will have to be deorbited safely, right?
So you could attach some kind of new boost mechanism on that fixture also.
A lot of people would love to take Hubble and just boost it to a really high orbit and let it sit there for 100 years until we figure out something better. Don't know if that's possible either, okay? That's something an Elon Musk would probably be useful for. All right, one last question? I got one last question. Is there somebody from the Maryland Space Grant Observatory here to take people across the street? Going once, going twice. No, there isn't. Was there? You in the back, did you have a question?
I'm going to apply for that position. I went to Friday night.
All right, it'll be open this Friday night? Yes.
I do have a question.
Yes.
A question. What do you think about the movie Interstellar?
It will surprise you to learn that I have not seen the movie Interstellar.
I have a theory of everything.
I have not seen the theory of everything. I
was
busy over the holidays getting ready for the American Astronomical Society meeting in Seattle. And also I promised the IMAX director I work with that I would see Interstellar on IMAX, not just go out to any movie theater, because Christopher Nolan, the director, loves IMAX and shot a lot of it with IMAX. And so I promised Tony that I would see it on IMAX, and I haven't taken the time to get there. But I will, now that Double A. Thank you all for coming. Next month. Decided they were going to do a joint proposal together. They pooled their ideas together, and that is what broke the logjam. That's what enabled enough political will to get Congress to fund the Large Space Telescope in 1977. Well, now that you've got funding and a plan, and it moves forward very quickly. In the 1980s, the telescope was built. In 1985, it was completed and construction. Here it is in Sunnyvale, California. And what is happening is it's undergoing a shake test here. Here's the guy in the bunny suit for scale. So this is a human size, and this is the size of the Hubble Space Telescope. It was certified for launch, and it was ready to go up on the space shuttle. Unfortunately, in 1986, we had the Challenger accident. The space shuttle program was grounded for several years, and Hubble sat in storage waiting to go up. Finally, in 1990, Hubble did launch. This is the launch of the Hubble Space Telescope. You'll notice there's another shuttle on the launch pad here. They were doing some testing there. There's only a few times in the history of the shuttle program when there have been two shuttles on the launch pad. They were doing testing here while they launched Hubble here. Here is the wonderful astronaut team that put Hubble into space. You will notice this gentleman right here. Does anybody know who he is? That's Charlie Bolden, the current NASA administrator. He put Hubble into orbit. So we hope that made him fond of our telescope. Here is the telescope sitting in the shuttle payload bay. you will notice that it fits very nicely in the shuttle payload bay. And that is, of course, by design, simply because we couldn't make Hubble any larger than what would fit in the shuttle payload bay. Okay? Would we have liked an even larger telescope? Of course we would. We're astronomers, and bigger is better when it comes to mirrors and everything, but we had a limitation. It's always good to have limitations. Our limitation was the size of the shuttle payload bay. The shuttle payload bay also carried aboard an IMAX camera, and this IMAX camera got this amazing shot of Hubble being set into orbit on April 25th, 1990. So, Hubble is finally up there from 1946 to 1990. That's all the precursor history to get Hubble launched. Well, what happens first? We get stories like this, instead of going and freezing your tootsies off in the observatory dome. But anyways, thanks to the Maryland Space Grant Observatory for providing that every month. Okay, so this is the point in the talk where I go to my news from the universe for January 2015. And our top story for tonight is, what? Are you kidding? I'm doing the main talk and had no time to gather news stories. Which I think is pretty much self-explanatory. So we move on to our featured speaker. All right. All right, our featured speaker tonight is myself, Dr. Frank Summers. Since we have so many new people here tonight, I'll give a little bit of my history. I'm an astronomer who got his undergraduate degree at Virginia Tech, go Hokies, and his graduate degrees at University of California, Berkeley. I then did postdocs at Princeton and Columbia. While I was at Columbia, I also was working at the American Museum of Natural History in New York, and I switched to full-time public outreach then. One of the 3 curators that built the Rose Center for Earth and Space in New York, the home of the brand new Hayden Planetarium in 2000. After building the Rose Center, I moved down here to Baltimore, worked with Hubble, and have been here for almost 14 years. I'm in the Office of Public Outreach here, and I get to work on all things Hubble. It's really a great job. I get to work on the news stories, I get to work on the website, I work on formal education, doing teacher training and informal education with museums and planetariums, and one of my specialties that I've developed while here is scientific visualization, having worked on 3 IMAX films, most notably being writer, science advisor, and scientific visualization supervisor on IMAX Hubble 3D 5 years ago. So, ladies and gentlemen, me. You already applauded, so don't do it again. Okay. Thank you for that wonderful and very knowledgeable introduction. I have an impossible task. I'm going to try to cover 25 years of Hubble in one lecture. And as I was getting this together, I found all sorts of cool stuff that I can't include in this talk because I spent this afternoon just hiding slides because there's so much really cool stuff. So I want to say, and in his exhibit, he has several works inspired by Hubble, and he will come and chat with some folks from here about the interplay of science and art on March 3rd. So that will be a lot of fun. If you want to find out things on our webpage, we have this Go link up here, but as usual, it's easiest if you just use your favorite search engine, look for Hubble Public Talks, and you should find this webpage. We'll has a list of the upcoming lectures, information about other things, and also if you see this link down here, this is the archive to our lectures that have been webcast by our team here for the past decade. We started doing this archive just before Hubble's 15th anniversary, and so we are approaching our 10-year anniversary of webcasts. So you've got 10 years of cool talks to catch up on if you haven't been here before. By the way, I always like to ask every now and then, all right, how many people have not been here before? Wow, that's a larger proportion than usual. I guess the 25th anniversary got your attention? Cool, great. Love to have that. Email. if you would like announcements, we have a email list that like twice a month sends you an email reminding you of the upcoming lectures. So far we've had a perfect record of no spam. Of course, now that this is being webcast, I know some hacker is going to go out there and find it and try and ruin that, but so far we're just fine. We have an email address, publiclecture@stsci.edu, which is the perfect place to send an email to sign up for these announcements, because we'll have your email return address and can add you to the list. You can also use this email for comments and or questions. Now, the one thing I don't know, oops, I'm sorry, we have our social media on Facebook and Twitter and Google Plus and Pinterest. And for me, I have my Facebook and Google Plus and Twitter, if you are so into following people in that way. One thing I don't know is the observatory. As a gentleman, I did not get an email today telling me whether the observatory would be open tonight. Usually they are, so this is a big question mark. And as someone down the front row goes, it's really cold. But you know what? The cold nights, you get the best seeing, okay? This is one of the unfortunate things of being an astronomer. When it's cold and the air is still, you really get better seeing. So I will ask again at the end of the lecture if there is somebody here to take you across. Otherwise, you will be able to go home and have hot chocolate. To those of you who have your favorite Hubble images, the astronomers who might be watching who have their favorite Hubble observation, probably because they were the PI on it, and those of you who have this idea in your mind of just something that was just really struck you, I may not include it in my talk tonight. Okay, I have not decided on the best Hubble images. I have not decided on the most scientifically important Hubble images. I have decided on a suite of imagery that tells a story, the story that I want to tell you about Hubble's 25 years. Okay, so with that apology out of the way, let's go for it. Now, of course, you can't do 25 years of Hubble without actually going back 70 years. 70 years to this man, Lyman Spitzer, and he was working at the Rand Corporation in 1946, and he wrote a white paper on the idea of a space telescope, the benefits to astronomy of having a space telescope. 1946, that was before we even had the space age. The space age didn't come until a decade later with the beach ball that was heard around the world, Sputnik, that orbited around and started the beginning of the space age. Well, Sputnik orbiting around the world had stimulated a mission of the creation of NASA in 1958. The National Aeronautics and Space Administration, this is their original logo. This is their current logo today, created in 1958. America gets into space. Well, very soon thereafter, at the very beginning of the space age, in 1962, this is the National Academy of Sciences building in Washington, D.C. It's just another, ceremonial building in D.C., but it has this wonderful statue of Einstein out front. So if your kids remember it, they went probably out and sat on Einstein's lap when they were there. But the National Academy of Sciences convened a panel on discussing the benefits of what they called at the time a large space telescope. Recommended that America should move forward on putting a large telescope into space. This, of course, ignited all sorts of ideas. Everybody has their wonderful ideas. And astronomers are great people, but I gotta say, astronomers tend to think that they're the smartest person in the room, so they tend to want to have their idea go forward. And this one want to have their idea forward. There's lots and lots of various ideas, various competing ideas, and not just in the US, but around the world. Well, the logjam was broken in 1976 when NASA, which by now had moved on to this wonderful worm logo, and ESA, the European Space Administration. Gentlemen, I am Dr. Frank Summers of the Space Telescope Science Institute, and it is my pleasure to welcome you here on this special night. As you can see, we are 1 week late. It is January 13th and not the second Tuesday, not the first Tuesday. But you can also see you got the really cool new seats and the wonderful new carpeting. They finished the auditorium retrofit, which is why they didn't let me have the public lecture series last week, which was good because I was in Seattle, Washington last week for the American Astronomical Society conference, so I wouldn't have been here had we held it last week. So it's great that both you and I can be here tonight, especially since I'm the speaker tonight. For those of you who came in, who haven't been here before, we have lithographs over on the table over there. If you did not get one on your way in, grab one on your way out. The lithographs are of the galaxy cluster Abell 2744, a very large cluster of galaxies, so large it produces gravitational lensing and is being used as part of the Frontier Field Survey, a little bit of which I will talk about in my talk tonight. Speaking of which, I am the speaker tonight, giving my 25 years of Hubble. I had actually expected to do this talk in April because the 25th anniversary is in April, but we decided to get the festivities going early. Right? We actually released the major 25th anniversary image last Monday at the AAS meeting in Seattle, and so I said, all right, great, if we're going to do that, I might as well go ahead and kick off the year with the 25 years of Hubble talk anyway. It's also kind of difficult to get a January speaker. Nobody wants to commit to doing the talk after the holidays. This has happened to me every year. I've been running the public lecture series for 13 years now. January and July are generally the hardest months to get people to come in and do the talk. Okay, upcoming, we do have other talks upcoming. Next month, February 3rd, Jason Tumlinson has given me one of the longer talk titles I've ever been given. From Cosmic Birth to Living Earth, the next great space telescope beyond JWST. And for those of you who know, JWST stands for the James Webb Space Telescope, and that's not launching until 2018. Well, Jason isn't satisfied with just looking forward a few years. He's going to look even beyond that to the telescopes that will come after the Webb telescope. On March 3rd, we have a very special event for you. We have teamed with the Baltimore Museum of Art, and they have a guest artist coming in, Dario Robleto.